Here we're continuing the notes from the first section where we're just picking up right where we left off. So these are the equations of the lines. And notice it's not in slope-intercept form. We don't have a y-intercept. Instead, this is more like point-slope form, where the point is the center. That's the point that we're identifying with the h and the k. And then we're packaging both slopes together with the plus or the minus. You don't really have to memorize if it's b over a or a over b. We're just going to go to the graph and we will count rise over run. The reason why this slope is a over b is because when we're looking at that box, we would be going up a units, because that gets us to the vertex, and then over b units. So that's why the slope is a over b. All right, so let's turn the page and get to the examples. We'll be taking a look at these first three examples here to graph our hyperbola. A couple other details. We have that Pythagorean theorem to help us show the relationship between the a, the b, and the c. This is different than the ellipse. With the ellipse, it was a squared minus b squared. Now it's a squared plus b squared, like we normally expect it to be. We can also use the eccentricity to measure its roundness. Really, we don't have round. It's more like how wide or flat it is versus how narrow or pinched together it is. Our value of c is always bigger because the focus is always farther from the center compared to the vertex. So that means we will always be bigger than 1. Again, that's different than the ellipse. The ellipse was an eccentricity between 0 and 1. The closer to 0, the more round it is. Here, our eccentricity is always bigger than 1. So the closer to 1, the more round it is, the way it's said here. By that we mean sort of narrow or pinched together. And if the eccentricity is much, much bigger, then it kind of widens out. It looks flatter, if you will. All right, here's example number 1. So I'm looking to see what letters in front. I see the x, and that means I'm thinking of the x-axis, which is horizontal. Therefore, this is also a horizontal transverse axis. Here's my h and my k, so positive 3 and negative 2. Remember, the a squared is always in front, the b squared is always in back, so that means a is 4 and b is 5. So let's use the Pythagorean theorem here to find the c. A squared plus b squared this time. So 16 and 25. So c is root 41. And to plot that, we'll turn that into a decimal value of about 6.4. Because of the scale of these things, I'm often going by 2's in both of my axes. So let's get our center down here at 3, negative 2. There it is. And then just for reference, here's my horizontal axis. There it is, okay. So the distance of A will take us to our vertices, so 4 units to the right and left of the center. And then the value of C, which is the 6.4, that'll take us to the right and to the center as well. That'll be the foci. There's all 5 critical points. Next, what we're doing is we're taking a look at creating this box. We know that the vertices are going to be creating boundaries of the box. So in this case, we have our left and right boundaries. We need to know how tall to make it. And that's what the value of B is representing. B is 5 in this case. So above and below the center, 5 units. Creates the top edge and the bottom edge of the box. And we're really looking to see where are those 4 vertices of the square. I guess it's a rectangle, right? And then we're going to use that to create our diagonal asymptotes. Now, when drawing the branches, they will go through the vertex. But don't draw it this way. I'm using tracing paper to show you my mistake here. Through the vertex, I see a lot of times branches kind of drawn like this, as if, hey, there's the direction, we're good to go. Just notice what's wrong here. If you take a look at the distance from that diagonal asymptote to the branch, notice how the distance is getting bigger and bigger, and that's not right. We are always approaching the asymptote. It's a barrier that we approach, but we can never reach entirely. So it's much better instead to make sure that your sides try to really kind of run parallel with the asymptote, like this. Over time, they'll gradually get closer and closer, but try to show them running parallel. So that sets the width, or how narrow or how flat it becomes. All right, so these are the other details. Our center is located at 3, -2. Vertices at -1, -2, comma 7, -2. The foci, again, they're a distance of root 41 compared to the center's location, so we have 3 plus or minus root 41, comma -2. And now for the equation of the asymptotes. We have 2 of them, so there's the plus or minus representing the slope, and what we're doing is we're counting the distance from the center to the top right corner. So we want to go rise over run, so up and then over. So up, that's the value of b. You could just count it here on the graph. That's a 5, and then to the right, that's 4. So up 5 over 4 means the slope is 5/4. There's the x minus 3, and then the value of k minus 2 at the end. The eccentricity then is c over a, so root 41 over 4, and my calculator will approximate that at 1.6. So it's fairly close to 1, in other words. All right, let's take a look at number 2. And really the key example in number 2 is working on completing the square and getting this set up in the standard form that we need. We have a 16y squared in front. There's the other term with y. There's the minus x squared behind. So let's bundle up our y's and our x's. 16y squared plus 64y minus the x squared plus 2x. Move the constant term to the right, so now it's a -127. Remove the common factor, so removing a 16, we are left with y squared plus 4y. Leave some space for your trinomial. Here, you might think there's no common factor, but we want to have that negative sign in the middle, and we want the x to be positive like the y is positive inside the grouping symbols. In other words, we're factoring out a -1. So positive x squared and a -2x. All right, let's complete the square now. For the y's, that value of b is 4, over 2 is 2, square that. We have a plus 4 in the trinomial, but it's 16 times 4, which means we're adding 16 times 4 on the right. For the y's, the value, for the x's rather, the value of b is -2, over 2 is -1, square that. It's a positive 1 in the trinomial, but it's really a value of -1 times 1, so we're subtracting 1 on the right-hand side. Let's factor each trinomial, y plus 2 quantity squared and y minus 1 quantity squared. On the right-hand side, that results in -64. That's a little bit unusual. Normally, we end up with a positive constant on the right. So what that means for us is we're dividing both sides by a -64 because we want to have a positive 1 on the right-hand side, like that. So not only are we reducing the fractions, but now the signs are going to be changing. The 16 over 64 is a -1/4. So we got a negative on the y's and a positive on the x's. Well, that means things are backwards now. We want the positive in front, we want the negative in the middle, so we have to take these two fractions and exchange their places. So here's the final form, x plus 1 squared over 64 minus y plus 2 quantity squared over 4 equals 1. Now we're ready. So again, notice that we have the x in front, there's the h, there's the k. This will be my a squared, this is my b squared. So because x is in front, I'm thinking of the horizontal x-axis, which means this is also a horizontal axis. H is -1, k is -2. lost my sign here. Hold on, I'm fixing a mistake. See right there where it says an x minus 1? That should still be x minus 1. That should be x minus 1, which means my h is positive 1. Okay, I'm caught up now. The a squared is 64, so a is 8. The b squared is 4, so b is 2. And now to find the value of c, here's our Pythagorean theorem. So c is root 68. And really I'm just turning that into the decimal value, which is about 8.2. All right, so with the center being at 1, negative 2, but a value of a which is 8, we're still going to need to set up our scale counting by 2's. There's my center, and again we have a horizontal axis. So to the right and to the left of that, my vertices are 8 units away. That's the value of a. So 2, 4, 6, 8, there's 1. 2, 4, 6, 8, there's the other. And then beyond that will be the foci, which is 8.2, which is hard to distinguish on this particular scale, but there it is. So that means we have this box set up by the vertices, so we have the left and the right edge. Now we want to find the height of the box, and that's going to be found by using the value b. So from the center, 2 units above and 2 units below makes for a very narrow box, and there are the 4 corners. We're not really supposed to be touching those asymptotes. We're supposed to be getting really close without touching it, so I kind of overdrew them, but I hope the shape makes sense. Our vertices are at negative 7, negative 2, 9, negative 2. Foci, 1 plus or minus root 68, negative 2. The asymptotes are plus or minus. Let's find the slope. We're going from the center to the top right corner, so we're going up 2 and to the right 8, so it's 2 over 8. Let's reduce that to 1/4. And then x minus 1 and a minus 2. Our eccentricity is c over a, so that'll be root 68 over 8, and that's almost 1. So both of these, of course, we had a horizontal axis. We were really using this as a demonstration on how to get that equation into the standard form that we needed. So we're going to finish up with example 3, which will have a vertical axis. So we'll take a look at that now. Again, we need to get this in standard form, so we're back to completing the square. Negative 4x squared minus 8x is in front, plus 25y squared plus 150y follows, and a negative 121 on the right-hand side. Factoring out a negative 4, the signs change. Factoring out a 25, we have a y squared plus 6y. We want to add 2. No, that's a 1. So 2 over 2 is 1, 1 squared, yeah, 1. But negative 4 times 1, that's a negative 4. And then with the y's, 6 over 2 is 3. Square that, it's a 9. So 25 times 9 is 225. All right, let's factor. So negative 4 in front, x plus 1 quantity squared, followed by positive 25 with a y plus 3 quantity squared. And the right-hand side turns into exactly 100. So let's divide everything by 100. Okay, once again, notice we're going to have a negative in front. So not only are we reducing the fraction, but we're going to shuffle the x's and y's around. It's the y's that will be positive, so let's bring that to the front. So y plus 3 quantity squared over 25 over 100, 94, And then we have the negative sign, followed by the x's, x plus 1, quantity squared, and that'll be a 25. So notice what we have now. Now we have the y is in front. So that tells me, hey, the y-axis runs vertically, therefore we will also have a vertical axis on our graph here as well. Notice now the h is back here. H is always behind the x, and the k is in front with the y, so that means the h is a -1 and the k is a -3. Again, we have the a squared is always in front and the b squared is behind, so that means a is 2, b is 5, and Pythagorean theorem to get the c. So c is root 29. Its decimal value is about 5.4. All right, we have all the values. Again, I will need to go by 2's on my scale, I believe. The center's at -1, -3. So there it is. And again, we have our vertical axis. So above and below that will be the vertices, which are a distance of 2 units away, the A. So there's a vertex, and there's a vertex. The foci are 5.4 away. And with that, we now have the top and bottom of the box. Right, so the vertices are creating the upper and bottom. We need the value of B, which is 5. So 5 units from the center to the right and to the left to create the right side and left side. All right, so there's our box. We want those 4 vertices. With a vertical axis, our branch opens upwards and downwards, so that means we have quite a wide-looking shape. All right, let's find all of these details. The center then is at -1, -3. Vertices are at -1, -1, and -1, -5. Foci are at -1, -3 plus or minus root 29. Asymptotes are, let me try that again, y equals plus or minus. So we want that slope, so we're going from the center to the top right corner. So up 2 and over 5, so 2/5. And then x plus 1 with a -3 on the outside. Our eccentricity, which is c over a, is root 29 over the value of 2. So that's about 2.7, right? So we said the larger the number is. Notice it's not like hugely large. It's just noticeably larger than what we've had for our eccentricities the past few graphs. It is bigger, and so the shape of the branches look wider or flatter, if you will.